Think about the last time you threw a ball. You knew, without thinking, how hard to throw it, at what angle, to reach a specific spot. You didn't calculate anything. You didn't measure velocities or work out trajectories. You just knew. Your arm knew. Your body understood the physics of motion perfectly. This confidence in your intuition feels completely justified. And in that moment, you predicted the future. Your intuition worked. But here's something worth thinking about. Your intuition is built for a world of throwing balls at close range, walking on flat ground, and moving at speeds that feel natural to your body. What happens when you leave that world behind? Today, we're going to explore something that every physicist grapples with: the question of why our instincts about how the universe works are so reliable in everyday life, and why they fail so spectacularly when we try to understand reality at larger or smaller scales. This isn't a story about humans being wrong. It's a story about understanding what intuition actually is, and what it's actually good for. Let's start by recognizing that your intuition about physics is not a mistake. It's a tool. And it's a remarkably good tool for the environment it was built for. Your ancestors survived by understanding motion, force, and cause and effect. If they didn't intuitively understand that a falling object would hurt them, they didn't survive long. If they couldn't predict where a thrown spear would go, they didn't eat. Intuition about physics was literally a matter of survival. Over millions of years, your brain evolved to be exquisitely sensitive to patterns of motion and force in the everyday world. You can catch a ball. You can predict where a rolling rock will go. You can feel the difference between stable ground and unstable ground. You have an intuitive sense of up and down, of fast and slow, of heavy and light. And here's the remarkable thing. All of this intuition is actually describing real physics. When you throw a ball, you're really doing the physics. Your nervous system, without conscious calculation, is solving equations about motion and gravity. You're executing complex mathematics with your muscles and your senses. So intuition isn't wrong. It's not a limitation we need to overcome. It's a success. It's a tool that works perfectly for the world it evolved to navigate. The problem is what happens when you step outside that world. Let me give you a simple example. Imagine you're in an airplane flying at a constant speed. You're sitting in your seat. You throw a ball forward, toward the front of the plane. Your intuition says, the ball will move away from you at the speed I threw it, plus the speed of the airplane. And intuitively, this makes sense. If you throw the ball forward at 20 miles per hour, and the plane is moving forward at 500 miles per hour, the ball should be moving forward at 520 miles per hour relative to the ground, right? Now imagine you're on that plane, and the plane shoots a light beam forward. Light travels at a fixed speed, roughly 186,000 miles per second. Your intuition says, the light beam should be traveling forward at 186,000 miles per second plus the speed of the plane. Except it's not. Light travels at 186,000 miles per second relative to the ground, regardless of how fast the plane is moving. Your intuition about speeds adding together, which works perfectly for balls, for cars, for everyday objects, completely fails for light. This isn't because light is strange or magical. It's because light is operating at a scale where a different set of rules applies. Your intuition was built for speeds that are slow compared to the speed of light. In that regime, speeds add together, and your intuition is right. But at speeds close to light speed, the rules are different. And that's where Einstein's relativity comes in. Your intuition didn't fail because you're not smart. It failed because your intuition is calibrated for a different regime of physics. Here's another example, even simpler. Imagine a very large object. Say, a mountain. If you're standing on a mountain, you feel gravity pulling you down. You feel pulled toward the center of the Earth. Now, imagine you're standing on the surface of a neutron star. A star so dense that it's compressed to the size of a city. A teaspoon of material from a neutron star would weigh as much as a small mountain on Earth. Your intuition about gravity says, you'd feel more gravity because you're closer to a more massive object. That's true. But you'd also be standing in a gravitational field so intense that the pull on your feet would be vastly stronger than the pull on your head. The difference in gravity between your feet and your head would be enough to stretch you like spaghetti. In physics, this is called spaghettification. This isn't because gravity is weird. It's because your intuition about gravity is built for everyday experience, where gravitational gradients are so small you never notice them. On Earth, gravity is roughly constant everywhere. The difference in gravity between your head and feet is negligible. But your intuition assumed that would always be true. It didn't, because you stepped outside the regime where intuition applies. These aren't failures of reason. They're not violations of common sense. They're reminders that common sense is calibrated for a specific set of circumstances. Now, you might be wondering, if intuition is so limited, how do we know anything at all? How do we trust science if it contradicts our instincts? The answer is experiments and mathematics. Experiments work because they don't rely on intuition. Instead of asking, "What does this feel like?" you ask, "What happens when I measure this precisely?" You set up a controlled situation. You measure the outcome. You compare it to your prediction. And if they don't match, you revise your understanding. This is how Einstein's relativity was discovered. Scientists made precise measurements of light speed. Those measurements contradicted intuition. Intuition said light should add with the velocity of the observer. Measurements said it didn't. Intuition was wrong. Reality was right. Mathematics works because it lets you extend reasoning beyond what intuition can reach. You can't intuitively understand what happens to objects moving at 99% the speed of light. But you can write equations that describe it. You can solve those equations. You can make predictions with precision that intuition could never achieve. This is the core of how science works. It doesn't start by trusting intuition. It starts by asking, what do observations and experiments tell us? And then it uses mathematics to organize those observations into a framework that works. Sometimes that framework matches intuition. Sometimes it contradicts it completely. But either way, the framework is tested against reality, and that's what matters. So what happens when physics moves beyond everyday scales? What does the world look like when you step outside the regime where intuition works? There are really two directions you can go. You can go to very large scales, cosmology, the physics of the universe as a whole. Or you can go to very small scales, quantum mechanics, the physics of atoms and particles. In cosmology, your intuition about space breaks down. You're used to space being infinite, flat, and unchanging. It has no center. It has no edge. Objects move through it. But in general relativity, space isn't a fixed background. It's dynamic. It curves. It expands. At the largest scales, the geometry of space itself is part of what's happening. Does this make space not real? It means space is more complex than your everyday intuition suggested. In quantum mechanics, your intuition about definite properties breaks down. You're used to objects having specific positions, velocities, and properties at any given moment. Those properties don't depend on whether anyone is observing. But at quantum scales, objects exist in superposition, multiple possible states at once. They don't have definite properties until they're measured. And measurement inevitably changes them. Does this make reality indeterminate or unknowable? It means reality is more subtle than your everyday intuition allowed. Quantum mechanics is the most precisely tested theory in the history of physics. It works because it accurately describes how nature behaves, even though that behavior doesn't match intuition. Now, I want to be very careful here about what I'm saying and what I'm not saying. I'm not saying that intuition is useless. Intuition is incredibly valuable. It's the first tool you reach for. It lets you navigate the world. It points you toward what matters. I'm not saying humans cannot understand reality. Humans absolutely can. We've built a detailed, precise understanding of how the universe works at every scale, from subatomic particles to the largest structures in the cosmos. This understanding isn't intuitive, but it's real. I'm not saying physics contradicts common sense. Physics explains common sense. It explains why certain things feel the way they do. It explains why your intuition works in the domains where it works. What I am saying is this: intuition is a specialized tool. It's perfectly calibrated for everyday experience. But the universe is far larger and more diverse than everyday experience. When you try to understand something outside the regime where intuition applies, something very fast, very small, very hot, very dense, very far away, you can't rely on intuition alone. You need experiments. You need mathematics. You need to be willing to revise your expectations. And that's not a limitation of human understanding. It's the strength of it. Think about how remarkable this is. Your brain evolved to understand falling objects and thrown spears. It's not equipped, by evolution, to understand how light behaves or how objects move near black holes or what happens inside atoms. Yet humans can understand these things. Not through intuition, but through a combination of careful observation, mathematical reasoning, and creativity. This is the great achievement of science. It lets humans extend understanding beyond the limits of intuition. Not by ignoring intuition, but by building formal frameworks that can be tested and refined. When you look at a physics textbook, what you're really looking at is a crystallization of human creativity and effort to describe reality as it actually is, rather than as it appears to be. So where does this leave us? It means that when you read about something in physics that sounds counterintuitive, that time slows down near massive objects, that particles can be in two places at once, that the universe is expanding, you shouldn't dismiss it as nonsense. And you shouldn't be confused about why it contradicts your intuition. Of course it contradicts your intuition. Your intuition wasn't built to understand those things. But it also doesn't mean the world is mysterious or magical. It means you're encountering something real that requires a different framework to understand. When physicists describe how light behaves, they're not describing something illogical. They're describing something that was discovered through experiment and is now understood through a mathematical framework that makes precise predictions. When physicists describe how time works, they're not describing something that defies reality. They're describing something more accurate than everyday intuition could capture. The universe doesn't care what feels intuitive to humans. It is what it is. And through science, we've developed increasingly accurate ways to describe what it is. Let me bring this back to something personal. You threw that ball at the beginning. Your intuition worked perfectly. And it still does. You can keep throwing balls, and your intuition will keep being right. But now, think about what you understand. You understand that your intuition works in a specific regime. You understand why it works, because your brain evolved to navigate that regime. You understand that beyond that regime, different rules apply. This understanding doesn't make you feel less confident in your intuition. It makes you more wise about when and where to trust it. And that's what understanding the limits of intuition really means. It's not about dismissing intuition. It's about appreciating what it is, using it where it works, and being willing to go beyond it where it doesn't. The goal of science isn't to replace human intuition with abstract equations. The goal is to understand reality as accurately as possible, using every tool available: observation, intuition, mathematics, creativity, and imagination. Sometimes those tools agree. Sometimes they contradict. When they do, we run the experiment again. We sharpen the mathematics. We refine our understanding. This process has taken humanity from wondering why the sun crosses the sky to understanding the nuclear fusion that powers it. From watching things fall to understanding that space and time are woven together. From seeing light as a simple beam to recognizing it as one of the most fundamental phenomena in the universe. None of this was intuitive. All of it is real. And that capacity to understand reality beyond intuition is one of the most beautiful features of human cognition. We are not trapped by the limits of our instincts. We can transcend them. We can know more than we can feel. That's not a weakness of intuition. That's the power of human understanding.